solving some problems on mean field control by using deep learning. So, as you have seen, a lot of talks in this workshop are about mean field problems. So, oh, I cannot move, yeah. Okay, let me just recall, in general, the two famous approaches on solving control problems, even in deterministic case, are the Pontryagin maximum principle and the Bellman's dynamic programming. And the dynamic programming approach requires that the system is Markovian. However, the maximum principle does not require that, but it leads to something complicated, which is an adjoint equation, and it's of type backward stochastic differential equation. However, the dynamic programming approach leads to something deterministic, which is partial differential equation. It's Hamilton-Jacobi-Bellman equations. But however, we can use also, or we can apply dynamic programming to some non-Markovian problems as well. In particular, to mean field problems. What we mean by mean field dynamics or making of loss of dynamics is like you have, for example, we have this large system of interacting particles that converges to the following system when n goes to infinity, and if we assume that the Brownian motions are IID. As I said, so here the dynamics depend, or the coefficient of the dynamic at time t depends on the state and also the expected value of the state. This is just an example of mean field dynamics, but you can even have more general dependence. For example, the law of the probability distribution of the state, and even you can have jumps in your dynamic. So this type of, or this is, as I said, call it the mean field dynamics or making of laughs of equations due to the dependence on these extra red terms. They can be the expected value or the probability distribution. So due to this dependence on these mean field terms, so these systems are not Markovian. So how to do to use dynamic program, how to apply dynamic programming approach to such a type of problems. Okay, so this has been really studied a lot in the literature, but here we will give like a slightly different approach than what exists. Okay, so a problem now of mean field control consists in the following. So we have a dynamics or controlled dynamics that's depending, or the drift coefficient of that dynamic depends on X, the law and the control. And we have also a diffusion coefficient. And also here we consider jumps. So we have even a jump coefficient. And there is the initial state that is given, and the mu t is the probability distribution of the states. And we have a cost function, so J of u, that is depending, or that is equal to the expected value of the integral of this running cost f plus this final cost g. And here the time horizon of the terminal time horizon is finite. So as I said before, so this is a non-Markovian system. So there are a lot of approach that people has used it in the literature. But here what we are going to do is that and also this has been considered also in the literature. So you you give a corresponding Fokker-Planck equation to the probability distribution of the state. And in that case, since we have jumps, so you will obtain like a Fokker-Planck partial differential equation. And here mu of gamma is the gamma shift of mu. Or for more detail, you can look at the paper by me and Oxondar. And this equation really is in a distribution sense. And these measures mu are, we assume that they are random measures, and then all finite, all random measures are distributions. So, and this also has been studied by Bokachev, Kurilov, Rockner, and co-authors, but they assume like the absolute continuity, but here we don't assume the absolute continuity of a measure, and we use some Fourier transforms to obtain this Fokker-Planck equation. So since now we have this Fokker-Planck equation, So we can define, so this is also the most different than what exists in the literature. So here, since we have an equation for the measure, so we can define like a new process Y that is dependent on the time, the original state X, but also on the measure mu, since we have an equation for it. And this process now Y is a Markov process. And then the original state is one of the components of that process. And then we can use, or we can obtain a Hamilton-Jacobi-Bellman equation. And also, yeah, here, they maybe write it, but we assume that the control is in feedback form, so which is dependent on time and X and the mu. So here you would have G of Y and instead and F of Y, and so on. So then we have this cost function plus this dynamics, then we can obtain the following theorem, which is an AGB equation for this optimal control problem of making Vlasov-Gem diffusions. That stated that if you have an integral differential operator, G of applied to phi, that is equal to this following equation. And then if we suppose that there exists, so this is like a type of a verification theorem. So we suppose that there exists a smooth function, phi of hat, such that the supremum of f plus g at the point phi hat equals to the following. So here in the left-hand side, really, we are taking like the supremum over all v. And then this first identity is simply saying that the optimal v is u hat. So for each, or for fixed y, you have this optimal v that is u hat. And that's why u hat is dependent on v. So for each v, you have an optimal v that is u hat of y. And then with that, the optimal v, the whole expression here equals to 0. And then this is like at the terminal time also, we have that phi hat equals to g, which means that if we put, because phi depends on s at the terminal time, capital T, it should equal to j. If this is satisfied, then u hat is exactly an optimal control, and phi hat is also the optimal value function. So then we can, why I'm recalling these issues, but we don't really need them later in the machine learning part, but I'm just recalling them to give you some particular examples that we can solve mathematically explicitly, but it's not always the case. Okay, so we can see that this very simple optimal conception problem where x of t is the cash flow at time t, and here rho t is the relative growth rate, and we subtract the relative consumption rate c of t times the expected value of x, plus some given volatility functions is sigma 0 of t times also the expected value dv, plus then the integral of the jump coefficient gamma, which is also supposed to be deterministic function times the expected value of x. Everything is integrated against the compensated post-random measure, and the initial value is assumed to be given as well. Okay, so here really what we are doing, so if we don't, if c equals 0 here, like the money will grow according really to the equation of x, and then if we add this c, is like we reduce the growth rate. So when you consume, you have to subtract something from the growth rate. And we want to maximize over C this profit function. So here we only consider logarithmic utilities. So here, so the logarithm of C times the expected value dt plus this lambda, which is the, we can call a utility parameter, which is supposed to be positive, because the lambda is like we encourage to save at the terminal time, because if lambda equals 0, then you don't save anything. You just consume as crazy. So due now to the dependence on this expected value on both the state and the profit, so we call this system a mean field also system, and then we want to apply the previous result to find the optimal conception rate. Okay, so here I will not really focus so much on details, And I think Van Talk, he presented so much important things. I will focus only on the application. So anyway, so then we can rewrite or we can obtain also here the corresponding Fokker-Planck equation that will satisfy this equation. And then if we set just E of x of t, the expected value, to be mu t applied to q for some, or for q equals to x, then we can also obtain the corresponding Hamilton-Jacobi-Bellman equation. So here, this is the supremum over all C of this should be equal to 0. So if we look here, C is only here, ln of C minus C times mu q dphi dx. And then we differentiate with respect to C, and we guess also that the value function has the following form for some smooth functions k0 and k1. And then we get the optimal conception process equals to that 1 divided by lambda plus capital T minus S. And this really shows that if we let S goes to capital T, then really we need lambda to be non-zero. Otherwise, this will explode. So this is just a motivation that we can really solve some particular examples explicitly, and then we don't really need to use any numerical methods. However, it's not always the case. Okay, before moving, I just want to mention something that comes to my mind here now, because if you see this, and this is what was presented by FAM. So if you have here, we can, because this, we have also extended this to have a Kamenoy's also dependence on X, and then you would get simply stochastic Fokker-Planck partial integral differential equation. So you will have some extra noise here. It's not anymore deterministic, and this is done in the paper with me and Oxendal. And okay, so now let's move to the main part of this talk, which is a numerical part. So I'm going to use deep learning, which is a subfield of machine learning. We know that machine learning also is a subfield of artificial intelligence. So why we are really going to use deep learning, really we will get the optimal control values for some particular examples. So this is very useful in optimization. Okay, so I will consider two different examples. So the first example is this optimal energy conception by the cortex neural network. So here is like you have, this is a simple model of neurons, where these rounds are really the neurons, and these arrows are the synapses that connect these neurons. And here, these neurons are connected via this, what we call the conductivity, UIJ matrix. Okay, so you have in general information or signals that are coming, and then this information or signals, they cannot really transfer it directly into the neurons unless it overcomes some threshold value. So here the input cannot be directly transferred. So this is one question, one of the problems we are looking for, under which, I mean, what's this threshold value? What's the minimum value of this input that we should get so that the information can be transferred into the neurons? And then the second question is, under which conditions this conductivity matrix should satisfy so that we can get the optimal energy conception of the cortex neural network. Okay, so we can formulate this problem as mean field control problem as follows. So then we assume that the dynamics of the voltage in the neural network, this is a real in some sense neural network, satisfies this following equation. So here the x of t equals to some drift that is dependent on the expected value of the product of x and u, dt plus some constant sigma 0, dv of t. And here the initial state equals to z times x. So usually a forward equation, the initial condition is given. But here we have this z, okay, if x is given, but then this z is some weight, which is unknown. So this is like the threshold value that we're looking for, the product. So then this is like you can see as a stochastic differential equation, but with the unspecified initial condition. So we don't know. And it's a part of our optimization problem as well. Okay, so here, yeah, we want to minimize this, cost function. So here, it's like a couple of processes. We have a control U, and we have also this weight, W. I call this product. Even if X is known, then the product is not known. So I call W, and then we have this, it's like a Stackelberg game problem, because we want to minimize both U and W. Okay, and yeah, yes, and this is like this problem, but okay, the initial here, the weight Z is a control, but it is just deterministic, but U is a stochastic control process. And then we would like to find a neural network that minimizes distance to a given terminal value F under the minimal use of energy. And this F is, we can call it target value. It can be even F capital T adapted, square integrable random variable, F capital T measurable. So this problem we have solved it like mathematically, but it leads to a very complicated formula for U. That's why we want to use deep learning to get explicit or to get value for the optimal U. Okay, so what we really do by using this deep learning, because our method in deep learning, we are not really going to use, by using deep learning here, you don't really need to know any optimization method at all. You don't need to know dynamic programming or maximum principle, nothing. So we will just plug in the whole system and we optimize it directly via deep learning. Okay, so here by optimizing, what I mean by using deep learning, so instead now of optimizing this control U, okay, you can look at U as a couple, U and W in our case, but here I'm just putting U in general, but it can be a part of this W since it is deterministic. You can look at if the U is D dimension, then U together with W is D plus 1 dimension. Okay, and then what the deep learning, what you're going to do is like you approximate this control by a function of the parameters of a neural network. And then instead of optimizing U, you have to optimize those parameters. In our case, we have the input that is composed of the time x of t and also the expected value of x of t, because our control U is given in feedback form. And since it is 3-dimensional, and okay, let's assume that we are working on 1 dimension. So the input contains 3 components, and then the output is only 1 that we are looking for. Then you should have 3 hidden layers here, because the number of hidden layers is not arbitrary. So it's 2 divided by 3 times the number of inputs plus the number of the outputs, minus the number, sorry, of the outputs plus 1. So then we have, since they are 3 minus 1, 3 times 2 divided by 3 is 2 plus minus 1, which is, sorry, 2, I always forget the formula, is 2 plus 2 minus 1, which is 1 plus, I'm sorry, I forgot the formula. Anyway, so this hidden layer, there is a formula for it that we can get. Or it's simply 2 divided by 3 times 2 plus 1, the output. Simply that, and then you get 3 hidden layers. Okay, and then what is there in these hidden layers? What we put there? Okay, so this input, you have really, you have this W and you have B, and there is this sign, sum. notations. So which are exactly what we call the weights, the biases, and then the activation function. So here you multiply these inputs by the weights, and then you add in the biases, and then you apply the activation function. And then you get a new input in some sense for the second hidden layer, that you will do the same thing. You multiply by the weights, you add the bias, and then you apply an activation function and so on. And this result is going feed forward into the neural network to get the output. And that is a type of feed forward neural network, because here we are going forward. And then to update the weights, you have to go backward later in the optimization. But this first one is just a feed forward neural network that we are using. More precisely, so as I said, the input now, we have this input, that is the time X and the expected value, and we want to get Q. And then to define the output, for example, by using this feed forward neural network, then you have to multiply, you have this activation function, and then the weights time the input plus the bias. And then this output, the first output would be the input for the second hidden layer. That's why y2 equals to this activation function, which is of w2 times y1 plus g2 and so on. And here we are using like different activation functions, which are tangent sigmoid function and just a linear one, the third one. So by using this, and then we want to, as I said, optimize the parameters of the neural network using stochastic gradient descent, but there are also other optimization methods that we can use. We just restrict ourselves to stochastic gradient descent, and then the parameters of this neural network are updated at iteration I+1 via this formula. So theta I+1 equals theta I minus eta, the gradient of j, theta I. So what we mean by this, what we are doing is, let me try to, I don't know, yeah. So for example, if we know that the minimum should be somewhere here, and then if you are, for example, starting from here, this is what explains, you can either go, for example, like that, and then you go down like that, sorry. Or you can use like a different point. If you are starting from here, and then you don't need to go, you go either like down so fast, or it depends, or you can go back again here and then you go down. So this is depending on this learning rate parameter eta, and it's not necessarily fixed. Okay, so then we could, because, okay, for constant u, we have calculated mathematically the results. I didn't really include, but then we, by allowing u to be stochastic and we apply this deep learning technique, we could obtain like also a better, in some sense, result, which means that our algorithm is like performing well. So here, this is like a draw of, or each curve here represents one realization of the Brownian motion, in some sense, one omega. And the thick curve here is the average. This black one represents the average over all paths. And this is the U. So this is the optimal, sorry, it's not, this is like X of t. And we have chosen this terminal F, if you remember here. We want to push X at the terminal time to be as close as possible as this target value F. So we put F to be 10, and then this is really clear here in the picture that at terminal time, because we took the time horizon called 3, and then at the terminal time, it's really conversion almost to 10. So this is the behavior of our X of t. And then the control U is also, at the beginning, it's like almost constant, and then it's getting varying to push it to get the minimum value. Okay, yes, this is the first example, and now I will move to the second example. So these examples are not really related to finance. But okay, this is like, since you have this initial state, we can look at this also as in the option pricing problem, because we are looking for this initial value. And we can assume that U is like the portfolio. And this is really related to these option pricing problems that has been studied in the literature. Okay, so the second example is this initial investment problem. So we suppose that the dynamics satisfies this equation. So you have A1 times the current state plus A2 times the previous values of the state, for example, x of t minus delta plus B1 times the expected value dt plus just a constant. But here you can really allow to have also more variables in dB, because it doesn't matter in the deep learning part what you have here. And the initial here x of t between minus delta and 0 equals to xi of t. So this is inside what we can call, or we want also to minimize g of xi, that is equal 1/2 xi square 0 plus 1/2 the integral from minus delta to 0 xi square dt plus 1/2 the expected value of this x at capital T minus g square. So this is like, there is a trade-off. It's like a linear quadratic problem. So, but the difference is that you have to push really from the beginning. And also we want to get x as close as possible to j. And this xi 0 we can look at as the measure of the energy. So we are looking for the best, in some sense, initial involvement. It's initial energy investment. It has nothing to do with finance. So for example, if you are ordering an equipment, arriving, for example, before starting time or before the system starts up, then you have to get it earlier. Okay. So here we also use deep learning, and we have like an input, and we have two hidden layers, and then the output layer together with the output, and we will also use a feed-forward neural network. It's almost the same as the previous case, because here also we are optimizing the initial state. But here is a function, it's not just a value, a given value. Okay, so this is a mean field with delay control problem. You can really solve mathematically by, for example, using the relation between linear controlled delayed equation and linear Volterra stochastic, or linear Volterra integral equation. This has been done in the literature by Lindqvist. I didn't really include so much mathematics here. Okay, but we could obtain some formulas mathematically, but as I said, it's quite complicated. That's why we moved to the deep learning, so that we can get a better performance. This is still a working in progress, this paper. So the idea is that we have to initialize. So the point is that, you know, in a deep learning, let me go back here, or in the previous case, so we give the input x of t as a given. So x of t is the input. Sorry, I'm just going back here to show you something. So x of t is the input that we give to a neural network. And since this initial value is considered as a part of a control problem, so how to do that? So that's why we need always to initiate these controls, u or the initial value here, xi. Okay, so because we want to get the data, and the data we get them from the state, from x. And to do so, we need to initialize these initial values randomly. And then this, as I said before, so this control will be like a function of the parameter of a deep neural network. And then we can get, for random size, we can get a state for each t and omega. And then by discretizing simply, this is like we are using the Euler-Mariema scheme. And then once we get X, we can compute J. And then we have, after we get a vector of J, we have to compute the gradient of J with respect to these parameters of neural network. Yeah, sorry, this should be really J of theta. And then we have to update these parameters of a neural network via stochastic gradient descent. And then we get the optimal values. So we stop up when this inequality is less than some small value of epsilon goes to 0 in some sense. And yeah, we get the result. Here we have got some some pictures, but they are not, they are quite okay. So because, you know, this is like, I don't know if we can yeah, we can consider this problem as a singular control problem. Because xi is a control, and then you can write dx of t equals to the whole thing. I mean, plus xi of t, from minus delta up to capital T. And then you can look at it as a singular control problem. And that's why the pictures are behaving like this. So this is for one realization xi, and this is for, I don't really remember, maybe 10 or 30 realizations. And this is the state. But this is still a work in progress, and we want to, we will try to perform it better in the future. Yeah, and that's it. Thank you for your attention.
Thank you, Nacira. Do we have comments from the audience?
I don't know if you can hear me.
Yes.
Okay. So I have a question on your first example, where you take as an input x and the expectation of x. But I think that the system is not Markovian if you take only the expectation of x. It's true only if the prime is linear quadratic, which is not the case in your example, I think.
You mean, but you can look at it as a linear, sorry. You
no, but
are
the
right.
dynamics.
I didn't write the state. Yeah, it's not the correct one. I'm so sorry. You are right. Yeah, this is nonlinear here in alpha. No, I'm sorry. It's a linear quadratic control problem. So this, I didn't write carefully. You can take the alpha. You simply consider the expected value of x times u here, dt, plus sigma 0 dB.
But you have to, but here is not linear because you multiply it by u.
Yeah, yeah.
So I think it's
you mean
the expectation of x is not enough to make the system Markovian.
Sorry, I don't get your last.
No, I say that so you say that the system is Markovian with respect to x and the expectation of x. But
I didn't.
I don't say it is. I'm sure it is not true in this example.
I didn't. I am here. We are not applying the previous result. So here we are using just a maximum principle approach.
No. But when you use your neural network, your input, okay. Yes, your input, you use x and expectation of x.
Okay.
So which means that you implicitly assume that it is Markovian.
Yeah. Yeah. But here, as I said, you know, we are in a deep learning. Really, we are. We don't need really to have Markovianity or anything, because, you know, we have x as data, and then we compute the expected value of x, and that are the inputs. So once you have x, you can have the expected value of x. So here there is no mathematical thing inside. So this is what I said. Our approach here is like, we only have the data that are x, and then we can compute e of x, the j, and so on. So we are not using any mathematical method here. It's like only the neural network that's working.
Yes, yes, and anyway, because the expectation of x is
I
deterministic,
understood exactly.
it's just a function of t, in fact.
Exactly.
Okay.
Yeah, thank you.
Thank you. Other comments? I have a small question of not really experts in your solution of deep learning, but how do you reckon that your solution is actually an approximation of the solution, the theoretical solution?
This is what I said from the beginning. So what we have is like we have computed for constant u the optimal value. That's the only thing. And then when we assume that u is stochastic, and then we use a deep learning, the numbers are the values are almost the same, or is better by using deep learning and allowing u to be stochastic. That's the only thing. But we are not really proving any convergence result. But I mean, there are some papers like I think Laurier, Carmona have proved some related convergence results for mean field problems. Yes.
Okay. Other comments from the virtual audience? No? No? Then we thank Nacira, and we thank all the speakers of this morning on this occasion.
Thank you.